So we are looking at the tectonic process, the so-called seafloor spreading, where the new ocean crusts keep forming at a regular interval. And we were discussing the so-called Gaia hypothesis, which argues that the rates of seafloor spreading have changed over time and that they have a feedback to weathering, which we looked at as these loops where seafloor spreading could either increase the CO2 input and create a warm greenhouse gas, increase temperature, rain and vegetation, which would increase chemical weathering, and that would increase the rate of CO2 removal from the atmosphere because weathering removes carbon dioxide, and that would reduce the warming. So you have a negative feedback. On the other hand, if the seafloor spreading rate was such that it reduced the CO2 input from within the crust or from volcanic activity into the atmosphere, it would create cold icehouse climate, which would decrease temperature. Every time temperature increases, you expect on the global average rainfall to increase, more humidity and so on. And rainfall would decrease if temperature decreases, and vegetation would also be affected negatively because of that, which would decrease the chemical weathering rates, which would decrease the CO2 removal rate. That means you are leaving more CO2 in the atmosphere, which would then reduce the cooling. So again, it's a negative feedback. Other examples where this thing seems to work, we will see that some of the changes are consistent with the Gaia hypothesis. So here is essentially what the Gaia hypothesis is saying, that the seafloor spreading rate affects the calcium carbonate dissolution, conversion into metamorphic rocks, or melting and emission of CO2 into the atmosphere, which would change the temperature, rainfall, weathering rates and so on. So there is a direct relation between a geologic process, carbon cycling and global climate. This is why looking at these things is important. One example where this seems to be working as hypothesized by the Gaia hypothesis is that if you look at the new mountain formations in various places like the South American Andes or the Indian subcontinent Himalayas uprising, then the uplift should lead to steep slopes, which would increase the erosion or mass wasting. So even if you have same amount of rain, when you have increased slope, then that rain, when it runs off, is going to erode more mass, and it will also lead to probably mountain glacier building depending on how high they are. For example, Kilimanjaro has glaciers as well, and the slope precipitation will also increase. As you imagine, as the monsoon winds flow into the Himalayas, the bottom of the foothills like Cherrapunji get huge amounts of rain, and the rain also continues on the slopes. So this would lead to increased rock fragmentation, increased weathering and CO2 removal, which would lead to global cooling. And this works exactly as hypothesized, as we will see, in going from the last hot house or the greenhouse that occurred about 100 million years ago to the cooling that has occurred over the last 50 million years or so. So here we are now looking at temperatures going from the present back in time. So 542 million years is where I said the post-Cambrian era starts. That's where the Phanerozoic or the visible life starts. The oxygen levels reached a certain threshold, not at the present level, but probably 30 to 50% of the present level. There was an explosion of more than 25 million new species, which is called the Cambrian explosion. Then you got Ordovician, Silurian, Devonian, Carboniferous, Permian, Triassic, Jurassic, Cretaceous, Paleogene, Neogene and so on. Do you have to remember all these things? No, I just remember them because I teach them all the time. So the temperatures varied, and there have been cold glacial periods too, at least, and this was a milder glacial period here before the hot greenhouse happened, when the dinosaurs were running around all the way to the polar latitudes, at least in the northern hemisphere. And then we are currently in a cold climate compared to this period, because now we have glaciers over Greenland Antarctica, and several mountains like Andes, Himalayas, Kilimanjaro, and so on. So, as I said, there are evidences in the system which tell us that they were glacial periods. It's not always clear how extensive they were, but if you find evidence of glaciation in lower latitudes, then it is fair to assume that they were probably nearly global. You cannot cover the entire planet with ice because the continued photosynthesis in the ocean would not be possible if ice cover was blocking sunlight going into the water. For photosynthesis, we need sunlight. So, it is not clear that the entire global ocean was covered. Maybe it was slushy ice and not solid ice, so some light could get through, and so on and so forth. These are essentially called as snowball Earth episodes, as I mentioned before. So, here potentially the evolution of vascular plants. So, the phytoplankton that were in the ocean colonized over land because of, let us say, changes in sea level or continental configuration, which increased the shelf area and so on. And once they settled on land, they had to start building hard materials so they could stand up and send their pollen into the air, and then they compete with each other and keep getting taller, develop hard material to be able to stand up, and so on. And photosynthesis kept on increasing, which means carbon dioxide kept on decreasing, and that would potentially lead to a glacial period. Then there is some warming again. As the plants became more abundant, another glacial period came, essentially because of some processes. The Carboniferous basically means a lot of the organic matter that was generated by photosynthesis somehow got buried and got converted into coal. So, most of the coal we dig up now comes from the Carboniferous period. So, if you bury a lot of the organic matter into the ground instead of letting it be respired back into CO2, remember that photosynthesis is CO2 plus H2O giving you CH2O, which is a carbohydrate molecule. Respiration is basically CH2O being converted back into CO2 and H2O. We can write those equations later in a separate module. So, if you prevent the respiration by hiding the hydrocarbon that is produced, then that carbon is getting sequestered, and that would also create a cooling and potentially give you a cold period. So, because of combination of these kind of vegetation feedbacks and orbital forcing, you got a very warm temperature, some of the warmest temperatures in the last 100 million years. Just around 100 million years ago, it is called the Cretaceous hothouse or the Cretaceous greenhouse, where we have evidence of the temperatures being very warm all the way into Arctic, Siberia, and so on. So, here it is showing highland area. So, the mountains were already in existence in the Appalachians and the Andes. Himalayas were not there yet because India is still here, several highlands here, and so on. And there is inundated areas. So, you can see that there was inland seas here, there is evidence of elevated sedimentary rocks and sand dunes here that confirm that in fact there were water all the way around here. This part was not yet together with Africa to create the Mediterranean Ocean, and so on. So, these were the continental configuration changes at the hothouse, but the evidence from high latitudes show that the leaves that were there actually corresponded to very warm temperatures, and there is evidence that dinosaurs were running around all the way into Siberia and northern latitudes north of the Arctic Circle. So, it is clear that there was no ice in the Arctic, there was no ice over the Antarctic, as you can see here, no ice here, no ice there, and probably no glaciers on any of these mountains. It was tremendously warm. If you now want to go back and put it together with your ideas of equator to pole temperature gradient and the amount of energy that needs to be moved, then the mid-Cretaceous equator to pole temperature gradient was very flat, much smaller than the present gradient. So, you can see that presently the northern hemisphere is going from tropical temperatures to minus 25 degrees centigrade in the northern hemisphere and almost minus 50 degrees centigrade in the southern hemisphere because of the asymmetry. So we have to move much more energy now from the equator to high latitudes, whereas in the mid Cretaceous you wouldn't have to move so much energy because the energy loss and energy gain were not as starkly different as it is now. But the other evidence that exists is the CO2 levels were more than 4 times the current levels. So if you assume the pre-industrial level of 280 multiplied by 4, then the levels of CO2 at the time were more than 1,000 parts per million by volume. That probably would explain why it was so warm, even though we cannot clearly explain why CO2 was so high in the atmosphere at the time. Okay, so that's kind of one example of climate change at a massive scale that is relevant. So again, to re-emphasize the role of CO2, all the global mean temperatures that we know of related to CO2 changes, there is extreme hothouse when the CO2 levels drop, and we get extreme greenhouse when CO2 levels increase. So right now we are at about 400 and we are headed in this direction. Where will we stop? At 600, some estimates are that we will hit 700. So you know that you are going to increase the global mean temperatures by quite a bit, which means the melting of glaciers is going to be almost guaranteed, which means we will see that there is lots of fresh water locked in those glaciers. If they melt, that will be released into the oceans and the sea levels will go up, right? So at least that's the direct consequences, and there are lots of other consequences as well. So when there was a hothouse and all the glaciers were melted away, then you have a high sea level because all the glacier water is now in the ocean. But when glaciers begin to rebuild, then the sea level drops. So the processes that were within the ocean, like the formation and deposition of calcium carbonate, which form mounds of calcium carbonate mountains in the shallow waters, those get exposed. So the so-called famous Dover Hills in the UK, in southern England and northern France, are essentially evidences that during the Cretaceous greenhouse there was tremendous amount of carbon dioxide in the atmosphere and the sea level was higher. Lots of calcium carbonate was being formed and deposited in the shallow waters. There is also reconstructions of the sea level that you can see, again going from the present back to about 120 million years ago, and this is the current sea level. So sea level was much higher. Somewhere around 50 million years ago, glaciers began to reform, temperatures began to cool, and sea level began to drop. So that's where we are at present. So these are two different estimates. They are slightly different. We don't always know what the errors are, because when the glaciers melt, the continents also move. We will see a little bit later on that when glaciers build, it's so heavy that it pushes the plate down where it is sitting, and the plate ahead of it actually gets pushed up. It's like, think of this as a plate. If I build ice here, this goes down and the front of it goes up, and when this melts, this begins to come up and this begins to go down. So relatively speaking, here sea level drops when this happens, sea level increases when this happens. So those kind of movements of the plates are hard to estimate. So sometimes sea level estimations have some errors, but there is no doubt that sea level was higher during the hothouse and has decreased during the cooling over the last 50 million years. So we don't have a firm answer on what caused the Cretaceous hothouse, but it's of interest because the CO2 is increasing now, and that points to a potential solution in the system. If we keep increasing carbon dioxide because of fossil fuel burning, what can happen? So these are the main processes that are considered for the explaining the Cretaceous hothouse. There were no major ice sheets, so sea level would have been up to 65 or more meters higher than at present. The thermal expansion, so when temperatures increase, the water actually is less dense and expands. So that contribution would have been about 7 meters. There is probably a minimal level of continents colliding and forming mountains at the time. So that would have given you tens of meters of sea level. during that time, and the deep sea fan sedimentation would have contributed something. The oceanic ridge volume was higher, and so on. So you take all the potential processes and you try to see what explains these levels of sea level change for those periods. There are uncertainties in all these processes, but the clear evidence that it was very warm and the carbon dioxide was more than 4 times the current levels. Okay. Obviously, the other big tectonic event that happened 65 million years ago was the meteorite crash, the asteroid impact that wiped out the dinosaurs. There are still theories being evolved as to whether it's the climate change that happened because of the asteroid impact that killed the dinosaurs, or whether there was an explosion of diseases and so on and so forth. But nonetheless, the evidence is clear that there was a asteroid impact. As we saw, it was seen in the iridium deposition in the mountain in Italy, and the crater impact is found in the Yucatan Peninsula in the Gulf of Mexico. So what are the processes that happen after the asteroid impact? Right after the impact, in just a few seconds to a minute, a shock wave is formed. Depending on how big it is, the shock wave can be very large or minor. So a lot of the water and rocks get vaporized because of the warm temperatures of the shock wave. Tidal waves and tsunamis get kicked off by the movement of the water by the asteroid hitting the oceans. There will be firestorms because of the warm temperatures and opening up and lava spewing out. There will be firestorms. From days to years, you will have lots of soot and dust in the stratosphere. So as the asteroid hits and it kicks up lots of dust, that dust is going to be strong like a volcano going all the way into the stratosphere, which means it becomes completely dark and everything will begin to cool down on the long term time scale. But in the meantime, a lot of the carbon dioxide and S2O4 sulfates that are kicked up are going to begin to acidify the lakes and the oceans, and the effect will continue for decades to centuries because of the extremely high levels of CO2 that are generated in the atmosphere by the crashing of the asteroid into the Earth's crust. So initially there will be a rapid warming. The dust and stratospheric cooling will create global cooling, but eventually you will come back to warming on times of decades to centuries. So is this of relevance to global warming? Well, if there's an asteroid crash, we'll have many other things to worry about rather than global warming, but at least we know the processes that occur this way. So that's an example of extreme hot house. But if you remember this temperature, we are since then cooling. So we are in this long-term cooling trend, and then global warming is happening here at the very end. So what is causing this cooling? Again, you have to put together a story based on all the evidences you can get: geological, geochemical, biological, fossil evidence, and so on and so forth. So if you go back to 65 million years to the present in the southern hemisphere and the northern hemisphere, there is evidence for warm temperatures in both hemispheres. The northern hemisphere, because it had more land, also has many fossils, palm-like trees at very high latitudes which are very tropical, hence you need very warm temperature. Crocodile-like ancestors in the north of the Arctic Circle, again warm water species found that far north, indicating no ice and very warm temperatures. And the local ice on Antarctica started to form somewhere around 35 to 40 million years ago from the geochemical evidence. The last of the trees on the Antarctic continent began to disappear, and the increase in Antarctica, ice on Antarctica has continued. We will see that there is some other tectonic process associated with this as well. And in the southern hemisphere, the glaciation in the Andes also started around 5 to 10 million years ago. In the northern hemisphere, broad-leafed evergreen and deciduous forests in the Arctic began to appear. So you went from warm temperatures to cooler temperatures and vegetation change. Then you started to spread cool, more colder species like spruce forests in the Arctic, and then the North American Eurasian ice began to appear somewhere between 5 to 10 million years ago. And the first evolution of our ancestors, from the chimpanzees and gorillas to our relatives like Australopithecus and Ardipithecus and so on, they also began to appear 3 to 5 million years ago, which is also related to another tectonic event that I will mention a little bit later. So here is the evidence of that was found north of the Arctic Circle, broad palm-like worm species fossilized back in the hothouse, and now we know that we have basically these so-called tundras which are grazed by these caribous and elks and other grazers that have lived in these cold climates or evolved to adapt to the cold climates over this cooling period. We can find many other evidences. So this is the estimated mean annual temperature from the outlines of fossil leaves that are found. Very briefly, if you look at the temperature range and the morphology of the leaves are basically trying to optimize loss of water. Pumping water from the deep in the soil to the top of the tree is a very difficult task. So the plant wants to be very careful about losing water. So the leaves are designed, so these serrated edges are basically better at not losing water, so keeping whatever little water they can find. Remember, in cold temperatures humidity is also very low, which means the contrast between the water in the leaf and outside can be very high, which means very rapid loss. In the tropics the leaves tend to be bigger and smooth edged because tropics are warm and more humid. So you can use this kind of temperature relation with the morphology of the leaves to reconstruct the temperature changes. So there is this evidence of a rather uneven cooling. So the cooling did not just happen straight like this. We used to cool and then there is a burst of warming, cooling and so on and so forth, basically because loss of the internal feedbacks will still be going on. Glaciers will be building, which will increase the reflectivity of the albedo, which will increase the rate of cooling, but some small tectonic change or change in the mountain or the opening of the Drake Passage or the Panama Canal or the rifting of the Africa and all sorts of processes would be going on, which would temporarily kick the system back to a warming. And you also have other changes like obliquity change, precession change and so on, which we will look at. So the combination of all forcings, volcanoes, tectonic processes, orbital processes would be going on, but it's pretty clear that in the last 50 million years we have cooled tremendously. Additional evidences come from what are called benthic forams or foraminifera. They are shown here, some examples, and they are recording either delta O18, which we discussed briefly and I will explain in a minute again, or the magnesium calcium thermometry. So basically, if you benthic means what? Pelagic means things that are in the open water of the open ocean. Benthic means those that are remaining close to the or on the bottom. Okay, benthos means the bottom. So these planktonic or benthic forams form shells which obviously are calcium carbonate, and when they form, magnesium is replacing calcium in the calcium carbonate crystal of aragonite and calcite. There are two types you can look up in the module, and that ratio of magnesium to calcium gives us a clear indication of what temperature existed in the benthos when they formed. So you can see that 65 million years ago the meteorite hit, and as we said, initial warming and then cooling and then bit of warming, and then the cooling started. Again, this is much smoother than what is estimated here. For various reasons, not all proxies give you the same time resolution. So this is a bit smoother, but you can see that it still has this uneven cooling, nonetheless a cooling, significant cooling. What is delta O18 telling us? Basically, if you compare to the value that existed 70 million years ago, remember how delta O18 works. When glaciers are forming, the evaporated water which has less delta O18 is going to keep losing delta O18 as it becomes snow over the glacier. So it is very enriched in O16, which means the ocean that is remaining, the bottom waters, are becoming richer and richer in O18. So look at the scale here, okay, this is negative here, in this direction it is increasing. So if it is increasing, that means more glaciers are forming, so the deep ocean is getting richer in O18, which means global climate is getting colder and colder. So both magnesium calcium thermometry and the delta O18 tell us that we have cooled quite a bit in the last 50 million years. So when you talk about climate change and global warming, you have to remember that we are in this long-term cooling trend, and then we are perturbing the system at the tail end of it since the Industrial Revolution. We will come back to this again and again. We will look at a couple of other tectonic processes before we close the section on tectonics and climate change. The geography of the continents was such that the Drake Passage, which is between the tip of South America and the Antarctic Peninsula, was not open till about 25 to 20 million years ago. So because of tectonics, when that split open, suddenly the circulation changed. So now you had created a channel where the water can keep going around. Okay, this is very important because in places where there are boundaries, when the winds try to put energy into the ocean, it is limited by how much space is available. Whereas if you have an open channel like this, then the winds can keep on churning the water till the wind forcing reaches all the way to the bottom. Okay, that's what happens in the Southern Ocean. But much more importantly, this circulation and the associated atmosphere ocean interactions essentially separated the South Pole from the rest of the global circulation. It created the so-called Antarctic circumpolar current and a jet stream that formed around here and a polar vortex and so on, that just trapped the climate within it and allowed it to cool and build the glacier. And as the glacier started building, the reflectivity increased, which further reduced the temperature because the energy loss is higher, and then it allowed more glacier to build and so on. So over this period, Antarctica has grown in glaciers till global warming started, where some of the glaciers have been melting because of all the warming. It's a bit more complicated in terms of which glacier is melting and which is not, which we will see when we get to climate change. So this is a tectonic process, but it made a tremendous change in global climate. Okay. The other thing that happened around 7 million years ago or so, 10 to 4 million years, so these ranges tend to be not very well exactly timed, the Isthmus of Panama was closed. So before that, these two continents were separate, and now they are joined together. That's why they had to open the Panama Canal to let the ships go through, but that is too small to affect the links between the Atlantic and Pacific Oceans. So you can imagine that if this was open, the circulation here would have been very different. Once it closed, the water that is flowing here, the warm tropical water, instead of going into the Pacific or the Pacific water coming into the Gulf of Mexico, this water started to go all the way to the north. If you bring warm surface waters, ocean waters to cold temperatures in the mid latitudes, you are going to increase the temperature of the atmosphere, because the atmosphere is feeling the ocean. If ocean gets warm, atmosphere also begins to get warm. And now you can go back and remember your fundamentals about what happens to humidity in a warm atmosphere. Warm atmosphere exponentially takes up more humidity, which means you began to increase evaporation over this region, the Greenland, Iceland, Norwegian seas. I'm sure you remember your thermohaline circulation, where we said that there is deep water forming, the North Atlantic deep water forming in this region. This warming and evaporation is very critical because evaporation produces lots of salt. Increased salt increases the density, and that water becomes heavy and sinks like a rock to the bottom, which is what we call deep water formation. So, the opening up the closing of the Isthmus of Panama affected the circulation not only locally, but also globally through this global thermohaline circulation. Okay. So, this is why these things are interesting. Why would thermohaline circulation be important for global warming? We will come back to it, but you can imagine that Greenland is sitting here with lots of glaciers. If glaciers begin to melt, that fresh water is going to be released into this region. If you release fresh water, then that will actually reduce the amount of salt you release when evaporation happens, which means you will reduce the amount of deep water that is forming. So, with the warming, the Greenland ice is melting. Now, you can use your ice and reflectivity or ice albedo relation to see whether this will go fast or slow. In the melting phase, if the ice melts, the reflectivity decreases, which means more heat is absorbed. So, more ice melts and more reflectivity reduction happens and so on. So, you will get a very rapid melting of ice. So, if Greenland begins to melt very rapidly, as it is already doing, the chance of putting more fresh water and perturbing this global thermohaline circulation is very high. Why is that important? Because we said the thermohaline circulation takes the carbon dioxide and the heat with it. 90% of the heat is going into the ocean. So, if you prevent the sinking of the water, you are going to reduce the sinking of heat, which means you are going to increase the rate of global warming with increasing CO2. This is why these past climates are important. So, did decreasing CO2 cause glaciation on Antarctica? There is some evidence based on all the estimated CO2 from various evidences from sediments and so on, that when you look from past 50 million years to the present, CO2 has definitely decreased. It has kind of remained around this value for the last 25 to 30 million years. What would have decreased the CO2? This is where we come back to the Black hypothesis, which said the seafloor spreading and mountain building can change the weathering rates and change global carbon dioxide. Correct? So, here are the current mountains. We have the Andes, we have the Rockies, we have the East African highlands, we have the Himalayas, and these all have currently glaciers, of course, in addition to Antarctica and Greenland. When did these mountains form? Does that explain any of this? Well, it turns out that they can. So, if you look at the movement of the Indian subcontinent from south of the equator to the Asian landmass, this is 68 million years ago, and somewhere around 35 million years ago, it began to crash and push into the Asian subcontinent, and you can see that kind of timing here. Okay, very critical. So, what happens when that happens, when a land crashes into a big landmass? Basically, you begin to push up the land that's already there. So, India is subducting under Asia, and Asian landmass is growing. So, the Himalayan mountains grew out of this process, and India continues to move north and subduct, which means the Himalayan mountains keep rising, and this is measured now very well, and the earthquakes that happen in regions like Nepal are basically related to this stress between the Indian subcontinent subducting under the Asian landmass, right. So, all these beautiful mountains, they are basically caused by this process, but what is also important is that when these mountains rise, all the material, especially organic material, the rocks, everything, they are exposed, right. But the more importantly, as India crashed into this position, the winds began to change, and the summer heating of the land, which is now so close to the tropics, to the equator, created this heat capacity contrast between the ocean and land, and gave us the monsoon circulation. So remember, if we are forming slopes and increasing rainfall all of a sudden, you are going to increase the sedimentation process tremendously, and you can see that this is showing the relative sediment flux going from 40 million years. It suddenly jumped around 10 million years ago when the monsoons kicked in their full present condition. They have changed over time, but essentially the seasonal monsoon of about 900 millimeters started around this time, and that increased the sediment quite a bit. What does that mean? That means the atmospheric carbon dioxide started to be taken down into the ocean by the rivers. So the Ganga Brahmaputra delta is very rich because it gets some of the highest rates of sediments in the world. So that would definitely explain the drop in CO2 because of mountain building. That explains that maybe Black hypothesis is on the right track. So just to kind of look again in terms of feedbacks, when uplift happened, a global cooling happened, that increased the ice, that increased the rock fragmentation and weathering. So the glaciers on Himalayas, Andes, Rockies, etc. would have done the same thing. That would have decreased further the global CO2, and that could have amplified the cooling further. So the cooling over the past 50 million years is definitely related to these mountain building processes that have gone on, with additional feedbacks in terms of, remember, there is also vegetation feedbacks, because a lot of the vegetation over East Africa, India, etc., even over Tibet and so on, they all evolved because of the monsoon. So Tibet is relatively dry, parts of India are relatively green forests, right? So you can now put that in the context of your Hadley cell knowledge. If you go back and look carefully at where the high pressure centers are, where the sinking air in the Hadley cell is causing dry climate, India should actually be in the same latitude. So the Middle Eastern deserts are on this side, and only we have the Thar desert here, but much of India is getting rich monsoons. So instead of being a desert, because of this monsoon, we are now getting lots of rain, right? And in fact, we are always suffering from water loss because of other reasons, but 900 millimeters of rain per year is a lot of rain. The deserts now go this way. Tibet is relatively dry, and the Mongolian and Gobi deserts are on that side. So the entire circulation, feedback, and the climate have changed together over this time period. So this is why the tectonic time scale climate change is interesting. Even though you can segregate it somehow from your main lesson plans, you should take the main changes that have happened and try to show the feedbacks, so that in the future climate, what are the feedbacks that will continue to work. This is what you have to figure out. Okay, so the take home points: on a billion-year time scale, evolution of the sun itself is very important, because sun was 70% of the current strength and 30% less power energy coming in. So we need something called the faint young sun paradox exists, which means if sun was less powerful, how is it that Earth had liquid water? Temperature would have been much colder. So you have to go through the calculations of energy balance to show that you will need methane or some other greenhouse effect to keep the temperature above freezing, and there are some calculations that already exist that show that you could have had enough methane to give you liquid water going all the way back when the sun was young and faint. Tectonic processes are important. We looked at everything from continents moving, mountain building, the openings of canals or opening of the passages. They all affect a climate. There is always interesting feedbacks involved, and as continents move, the critical question is what configuration is most ideal for growing glaciers. So sitting at the pole like Antarctica does obviously is very helpful for building glaciers, but Antarctica has been sitting there for a long time, and the glacier only started building about 35 million years ago. So it doesn't mean just because there is land there will be glacier. other things matter as to how much CO2 there is in the atmosphere. So during the Cretaceous 100 million years ago, the CO2 was more than 1,000 parts per million by volume, so there was no glacier on Antarctica, and only the cooling and the drawdown of CO2 by the mountain building processes and the Gaia Hypothesis gave us glaciers over Antarctica. So those are important processes. Evolution of life has critically been deterministic in terms of the oxygen levels in the atmosphere. So life and climate have co-evolved. If you are really curious, there is something called Gaia Hypothesis that you can look up, Gaia, which in Greek means Mother Earth. Gaia Hypothesis basically says that life evolves to control its environment. Is this true? In some limited cases it seems to be true, but not on a global scale. Nonetheless, it does build on the idea that life itself has been important for the composition of the atmosphere. So evolution of photosynthesis, vascular plants has been very critical for the evolution of the atmosphere and the current levels of oxygen in the atmosphere. That's something also to remember. Closing and opening of the passages have altered Earth's climate. The most critical one is the opening of the Drake Passage and isolation of the Antarctic continent and building of glaciers and the circulation around it. It still plays very important role because the ozone hole, if you look carefully, is right over Antarctica. So any chlorofluorocarbons that make into the vortex remain trapped there and they keep on destroying the ozone. So the ozone hole is very strong over the Antarctic continent because of this peculiar circulation that is related to the Drake Passage opening up. The current global warming is occurring in the context of this global cooling. So we are in the long term 50 million year time scale cooling, which we just looked at, and at the tail end of it we have started this industrial revolution, and we will see that actually we might have started global warming even earlier when we started large scale agriculture and deforestation and so on. So what does that mean? That means if we will see later on when we do orbital scale climate change that there are ice ages happening. Were we going into an ice age, and is global warming actually delaying the next ice age? These are the kind of critical questions we will learn in the next section when we get into orbital scale climate change. See you next time.